Hey everyone, welcome to Calculus 1 Exam 1 Review. This is version A. And so just to remind you about some things. So this is our online math resources for student site. This is where this is all taking place. It's live right now, but of course you're watching the recording. So if you just click on Calculus with Analytic Geometry, and right in here, this is where you can see all those live sessions that we're having this semester. And right over here is that test review materials. So in here, you can see there's our blank version A document, which I'm going to have displayed as we go through. We are working on the solution guide right now. So once this video is done, I will post that. And then here is the video that you are currently watching. So always come back here if you ever need to see all this information again. And as we move throughout the year, we will complete the rest of these version A's that you see there. So with that being said, let's do the exam 1 review. So here's our first question. And it says, sketch the graph of an example of a function f that satisfies all of the given conditions. So I'm going to do a little bit of writing where I'm going to write down these limits that we have going on here. So I got the limit as x approaches -1 from the left of f of x, and that is equal to 0. I've got the limit as x approaches -1 from the right of f of x, and that is equal to 1. I've got the limit as x approaches 2 of f of x, and that is equal to 3. And then I have two defined function values where f of -1 is equal to 4 and f of 2 is equal to 0. So we're going to take this information and we're going to create a lovely picture. So there's all that information we just talked about. I'm going to draw a simple little graph down here. And your graphs do not have to be anything spectacular. Okay, because again, this is going to be a rough sketch because we don't know what f of x is. So the first thing is that I generally ask my students is like, what are the values that we care about? Well, right here, you can see these x values. We care about -1 and we care about 2. So I'm going to put in like a little -1 right there. And then I'm going to come over in here and put in my 2. Okay, see, nothing crazy. I'm just making a simple graph. And I'm only really worrying about the numbers that I care about. Now over here, remember that limits are all about what the y values are doing. So we got some y values here that we care about. So let's start dealing with those y values. And just so you know, we got like 0, we've got a 1. So I'm going to go ahead and put some of these in. We got a, well, we don't have to worry about the 2, but we do have the 3. So I'm going to take that 2 off there. And we do have a 4 to worry about. So let me erase that 2. I'm going to keep the little tick mark for it, but I'm only going to highlight the numbers that we really care about. Keep this just a little bit taller. So 3 and 4. Those are really the numbers, and also 0, but that's just like the x-axis, so it's no worries. So let's start working here. Let's work with this first limit. So remember, limits are all about what the function is doing, what the y values are doing as the function approaches this value. So when we deal with these limits, these are going to be open circles for us because limits don't tell us what is happening at -1. It tells us what is happening as we approach -1. Now we might fill those circles in, but for right now, when we deal with these limits, let's make them open. So as x approaches -1 from the left, we're going to 0. So I'm going to put an open circle here at 0. And then as x approaches -1 from the right, we're going to approach 1. So I'm going to make an open circle up here at 1. Now, to determine whether these are closed or not, you look at where it's defined. If it is defined, and right here it says at -1, we're going to be defined at the number 4. So this is where my closed circle will go, if it exists, because we don't have to be defined. So there's my closed circle. So these will remain open. Okay. So we've got that taken care of. Now let's take care of this limit. Now this is what we call the two-sided limit. So this means that as x approaches 2 from the left, it's going to 3. And as x approaches 2 from the right, it's going to 3. So at 2 here, I'm going to just come up here and put an open circle and know that my function, whatever's happening, is coming in towards this from the left, and it's coming in towards this from the right. Now, do we fill this in? Well, let's go look at where it's defined. Well, f of 2 is 0. So that's where we're going to put the point at 2, 0, the closed circle. So that will stay open. So now all we have to do is draw in our function. So we're going to work from left to right. So from the left, my function has to hit 0. So I'm going to just draw in my function, and it's going to look like this. Now, again, I could have drawn my function any way I want. I could have had my function come in from the top. I could have had my function come up, down, as long as it comes to -1 from the left. So there's lots of ways to draw it. But as I always tell my students, I want you to think of this as a kiss. Okay. Keep it simple, silly. Okay. Don't do anything crazy. Just draw a simple function. Don't do all the loopies and all this stuff, because that's where sometimes we as math students get in trouble when we try to be fancy. All right. Now, the next one says from the right, I should be approaching 1. So my function is going to be coming right off of this point. Now let's see who we got to connect to over here. So right here, it says my function should be going to, as x approaches 2, should be going to 3. So I now know that these two circles, these 2 points, need to be connected. And I'm just going to draw a straight line to it. I don't need anything fancy. Now, again, you could have swooped down and up to it, swooped up and up to it, or gone up, down, as long as these 2 points were the ones being connected. Okay. And then last but not least, this tells us the other side of the function, because remember, it's double-sided. It's a two-sided limit. And it just says our function is coming in towards 3 from this side. So I'm just going to make it swoop down to it. I could have gone and swooped out, downwards, or again, up and down and all that stuff. But again, I like to keep this as a kiss, as in keep it simple, silly. And there's our function, or a version of our function. And everything up here is being met by this. You can double check it. Yay. Moving on. Number 2. So number 2 is all about our little graph here. Okay. We've got some parts to it, and that's okay. So we want to, for the function a, whatever a is, whose graph is shown, we're going to use this graph, state the limits. Okay. If the limit is infinite or negative infinity, make sure that we do that. We state that. If it does not exist, we'll write D and E, and then we're going to answer these questions. Okay. So our first limit, and I'm not going to rewrite the limit, and I'm not really going to show much of the page over here. I'm just going to write the answers down, because this is all based off of the picture. So right here, it says, what is the double-sided limit of -3? Now, remember that limits only exist if the left limit and the right limit end up being the same answer. Okay, sometimes they're the same value, but remember, infinite and negative infinity are not really like a number answer. They represent a large range of answers. But if the two limits have the same type of infinity, then we can talk about that limit existing. So remember, double-sided limits only exist if both limits coming in from the left and the right are the same. All right. So this is a double-sided limit. So let's see what's happening over here on the left side of -3. So as we come into -3 from the left side, my function is shooting straight up. So that means the left limit as x approaches -3 is positive infinity. From the right side, as my function comes into -3 from the right, again, my function shooting straight up. So that means the right-sided limit as x goes into -3 is positive infinity. Since the left limit is positive infinity, the right limit is positive infinity. Both of them are the same. That means the double-sided limit as x approaches as x approaches -3 for our function is positive infinity. All right. So B and C are taking one-sided limits. So what happens as we approach 2 from the left? Okay, so here's 2. So here's our function. As we approach 2 from the left, our function is shooting straight down. So that answer is negative infinity. So as we approach 2 from the left, my function is negative infinity as the limit. C is what happens at 2 from the right. So as my function comes in from the right, we're shooting up towards positive infinity. So they didn't ask this question, but I'm going to go ahead and ask it. Since the left is negative infinity and the right is positive infinity, what do you think the limit at 2 would be then? It doesn't exist, Mr. Armstrong. That's right, because these are two different limits. Negative infinity, positive infinity are not the same. So you are absolutely right when you say that if we looked at the double-sided limit at 2, it does not exist. Cool. You guys are so smart. All right. So let's continue on. D, again, is a double-sided limit. So let's look at what happens to our function as it approaches -1 from the left. So as we go to -1 from the left, my function is shooting straight down. So that's negative infinity. As my function approaches from the right, my function is shooting straight down. Negative infinity again. Since the left limit is negative infinity, the right limit is negative infinity. The limit of our function as x approaches -1 will be negative infinity. And then part E is pretty straightforward. It just wants to know what numbers have vertical asymptotes. So you just kind of, really look at your graph. But it's also around, all of our asymptotes are around where we have limits going to infinities. So we definitely have a vertical asymptote at -3. So that's one of our answers. Then you'll put a comma and you'll put another vertical asymptote at -1. And then you'll put a comma, and then we have one final vertical asymptote at 2. And that is the answer for part E. -3, -1, -3, -1, and +2. There's all of our hard-earned work. All right, moving on to question 3 out of 14, if I didn't say that before. Question 3 out of 14. And again, another one of these problems where we're really going to just use the graph. There's not really any work to show, and I'm not going to rewrite the limits on my piece of paper and all that jazz. So let's talk about this. So we just want to state the limit if it exists. Okay. So again, double-sided limit. Double-sided limits only exist if both the left and the right have the same limit value. So we're going to look at 1. So here's 1. As we come in from the left, the y values are going towards the value 2. As we come in from the right, the y values again are going to 2. Since the left goes to 2 and the right goes to 2, the limit of f of x as x goes to 1 is 2. All right. So let's take a look at B. So what is the limit as we come in from the left for 3? So as we come in from the left for 3, our y values are honing in right here. And that is the answer 1. As we come in from the right for part C, as we come in towards x is 3, our y values are honing in right here, which is 4. Okay. So now it wants to know what's the answer to the double-sided limit. Well, we know that the left limit was 1. The right limit was 4. Since they're not the same, the double-sided limit does not exist. It's a DNE. And then last but not least, they want to know, well, what is the answer when f is 3, or sorry, when x is 3? Because remember, limits don't tell us what's happening at that number. It's telling us what happens to the y values as we get closer and closer and closer and closer and closer. So what happens when f is 3? So is it defined, in other words? So when f is 3, we have a point right here. And that's at the y value 3. And so there are what all the answers look like. 2, 1, 4, does not exist, 3. All right, moving on. Number 4. Doing a great job. So in here, this is where we're going to use a lot of those limit laws we talked about. So I'm going to write my limits out so I don't have to jump back and forth very much. So the limit as x goes to 1 of f of x is equal to 1. The limit as x goes to 1 of g of x is equal to negative 2. And the limit as x goes to 1 of h of x is equal to 0. So I'm going to work each one of these, and I'm going to show you those limit laws in action. So that way we can break down how everything is working, even though I know a lot of you kind of know some things about like direct substitution and things like that right now. But again, remember, you're showing me what you can remember throughout the entire module 1. So here's the first limit that we're dealing with. And remember, we have some laws that say that if I have 2 functions that are being added, I can basically, and again, this is bad mathematics, but it's kind of like we're going to distribute the limit function to each one of these. That's not really what happens, okay? But it's kind of like that idea. So we can take the limit of each of these functions and then add them together. Also, remember that if you've got a constant times a function dealing with the limit, that constant can be shifted out front. Okay, so it looks like this when we really expand it out. The limit as x approaches 1 of f of x plus 2 times the limit as x approach 1 of g of x. So those are our limit laws in action. And now it's kind of just like substituting in, because we know what happens when the limit as x approaches 1 for f of x. We know that that answer is 1. So it's like substituting in. Plus 2 times, and we know this limit. As x approaches 1 for g, it's negative 2. And now we can get the answer that I'm sure you all knew from the very beginning was -3. All right, let's take a look at part B. So part B says, and again, this moves straight down, and then we'll come over to this column and move straight down. So the limit as x approaches 1 of g of x, and we're cubing it. Okay. So again, we have a law that says if I have a function that's being raised to the power, I could actually slip the limit inside and find the limit of the function and then take it to a power. So we can shift the power around the entire limit. So that looks like this. So here's my little limit law in action. See, I just moved the power to the outside. So now we actually know what this is, and then we cube it, and we got our answer. Because the limit for g of x, as we said before, is -2. So all we have to do is cube that, which gives us -8. All right, C. C says we've got the limit as x approaches 1 with a square root of f of x. Now, there are two ways that you can approach this one. Okay, we do have a law, a limit law that is a lot like this, where if we have square roots going on, I can just slip the limit under the square root and think of it like this. The limit as x approaches 1 of f of x. But also remember back in college algebra and back in all those algebra classes you took before, this is really, when you deal with radicals, it's really a power in disguise. So you could also think of it as just another power 1. So remember, this is f of x, and a square root is really just a 1/2 power. And again, that also illustrates, because if I put the 1/2 power outside, oh, well, the 1/2 just represents the square root. So it's still the same thing. So it's your call on how you want to think about it. So I'm just going to keep it like this. And all we got to do is plug in. We know that the limit of f of x is 1. So what is the square root of 1? It's 1. Okay. D. D, we have the limit as x goes to 1 of 2 f of x all over g of x. So again, very much like the addition that we had up above, how it's like distributing the limit through. This is the same idea. The limit can be distributed to the numerator and denominator. And again, we got a constant, so we'll just slip that out in front. So it really looks like this. 2, the limit as x approaches 1 of f of x all over the limit as x approaches 1 g of x. And again, we just plug in the numbers we know. So this is 2, the limit of f of x is 1, all over the limit of g of x is -2. So in the end, you end up with -1 as our answer. Okay, nothing crazy. So I got to move on to another piece of paper. Still doing this, though. Still doing some limit laws. So number 4, part E. So part E says, let's do division again. So this time we're going to take the limit as x goes to 1 of g of x over h of x. So you already know that the limit's just going to go to both of these. So applying my limit law, I get the limit of g of x all over the limit as x goes to 1 of h of x. So the first time we get to use h, yay. So we know the limit as x goes to 1 of g, and that was -2. And we know the limit as x goes to 1 of h of x was 0. So you got -2 divided by 0. That means that this limit does not exist. Do not say undefined. Say does not exist. Okay? There's a difference between undefined and does not exist for us. And last but not least, we're going to use all three functions this time. So the limit as x goes to 1 of g of x, h of x, all over f of x. So again, you got a little multiplying up here, and all that's going to happen with my limit laws is both of these are going to get their own limits, and then the limit is also going to go to the denominator. So using my limit laws, it actually looks like this. Limit as x goes to 1 of g of x. Then I got the limit as x goes to 1 of h of x. And all of those two are over the limit as x goes to 1 of f of x. So all we have to do is plug in what we know. We know that g of x is -2. We know that h of x is 0. And we know that f of x is 1. And in the end, we find out that the limit equals 0. And there you go. Just applying limit laws. That's all this was about. Limit laws and figuring out some answers. Yay. So let's talk about number 5. So we got the limit as x approaches 6. And we got 4 minus 1/3 x is the limit that we want to take, the function that we want to find the limit of. All right. So a couple things. You can do direct substitution on this. You can also use our limit laws because this is like its own little function. This is like its own little function. It's very much like part A that we did on number 4. Okay. But you can also do direct substitution on this because remember, we can direct substitute in if our value is in the domain of this function. And this function is linear, which means the domain is all reals. So 6 is definitely in that domain, and we can direct substitute in. But I want to show you the limit laws, which will really lead into direct substitution anyway. So if I apply my limit laws to this, that means I'm going to take the limit as x goes to 6 of 4, the constant. And then this is a constant times our function. So I'm just going to move that 1/3 out front and take the limit as x approaches 6 for x. See, there's our limit laws at work. Everything that we just kind of did in number 4. All right. And what is the limit as x approaches 6 of a constant? Well, it's just the constant. So that limit is 4. Minus 1/3 times what is the limit as x approaches 6 of the linear function x? Well, it's just whatever value that is, because the x value is the same as the y value in that function. So the limit as x goes to 6 of x is 6. And you can notice that if I just direct substituted in, that's where I would have been at. And so in the end, what do we get? Well, 1/3 of 6 is 2. 4 minus 2 is 2. Number 6. So we have the limit as t goes to 7. And we have t squared minus 4t minus 21 all over t minus 7. So we want to find the limit of this. Okay, but that's not too hard to do. All right. You can try direct substitution, but unfortunately 7 is not in this domain because it makes that 0 down there. So you got to try something else. So remember, if direct substitution didn't work sometimes factoring helped out. Okay, so take a look at this numerator, and does it factor? Absolutely. So if I factor that numerator, I get this. T minus 7, and then t plus 3, all over t minus 7. And what do you notice? These two are going to knock each other out. So another limit we could look at that will be the same answer as this guy is the limit as t goes to 7 of t plus 3. And again, I could use my limit laws and have the limit as t goes to 7 of t plus the limit as t goes to 7 of 3. Okay, but let's just go ahead and direct substitute in because we can do that now, even though it wasn't a part of my answer in the beginning. The 7 was it, or sorry, not answer, domain. So 7 plus 3 equals 10. And there we go. All right, number 7's. Okay, so number 7. This is the squeeze theorem in action. So we have this 6x less than some sort of g of x less than or equal to 3x to the 4th minus 3x squared plus 6. And what we want to know, what is the limit as x approaches 1 of g of x? So you can see a little bit better. So we want to know this limit. Well, according to the squeeze theorem, if I have a small function and a large function, and there's another kind of like, you can call it the medium function, is between it. If these two outside limits equal each other, then this has to have the same limit as the outside two. So what we need to show then, we need to show that the limit as x goes to 1 of 6x, is it the same as the limit as x goes to 1 of 3x to the 4th minus 3x squared plus 6. If these two have the same limit, then g of x has to have that limit by the squeeze theorem. So let's take a look at these two. So I got to continue on to another page. That's okay. So let's find the limit as x goes to 1 of 6x. Well, this is a linear function. The domain is all reals, so we can do direct substitution. So the limit of this is going to be whatever 6 times 1 is. Well, 6 times 1 is 6. So as long as this next limit, which is the limit as x approaches 1, of 3x to the 4th minus 3x squared plus 6, as long as this equals 6, then we know the g of x limit as x approaches 1. It will have to be 6 as well. So let's check. Again, this is a polynomial, and polynomials all have a range, or sorry, not a range, a domain of all reals. Okay. So we know that 1 is in this domain, so we can do direct substitution. So let's take 3 times 1 to the 4th minus 3 times 1 squared plus 6. Well, 1 to the 4th is 1. 1 times 3 is 3. 1 to the 2nd is 1. 1 times 3 is 3. So 3 minus 3, 0. And 0 plus 6 is 6. They equal each other. Therefore, by the squeeze theorem, the limit as x approaches 1 of g of x must equal 6. If they didn't equal 6, and without knowing what g of x is, we couldn't answer this question. Okay? And there we go. Number 8. We're doing great. All right. So we're going to look at this graph. Okay? And we want to answer some questions about continuity. All right. So first is part A says, looking at the graph, tell us the numbers where G is discontinuous. So we're looking for holes. We're looking for vertical asymptotes. We're looking for some of those removable and jump discontinuities, things like that. So part A, where do we have holes? Well, here's one place where we are discontinuous. Discontinuous also means that when we draw our graph, we actually have to kind of lift our pencil to complete the graph. So a hole is going to make us lift our pencil. So we know one of our values is at -2. Here we've got a vertical asymptote. We're going to have to lift our pencil because we got to finish this graph and then pick up and do the next side of the graph. So we got a vertical asymptote there at -1. Okay. We have another jump discontinuity right here. Okay. At 0. We have another jump right here at 1. So we have 4 discontinuities that we're dealing with. -2, -1, 0, 1. So there's the answer to part A. Now, part B, we want to talk about each one of these. And what part B is asking is it continuous to the right, to the left, or neither? Okay. So in order to tell if something is continuous, you need to take the limit at that number from the left and take the limit at that number from the right. And if the limit equals where it is defined at that number, then it is continuous. Okay. So for instance, -3 is continuous from the right. Just kind of giving you a quick example. -3 is continuous from the right because the limit of the y values from the right are all coming in right here at, let's just call this +2. Just say this is +2 up here. So all the y values are coming in at +2. And what is f of -3? It's +2. So because it is defined and it is equal to where the limit is also equal. So the limit coming in from the right was +2. F of 3 is +2 because both of those are the same. That's why I say this is continuous from the right. Okay. All right. So let's look at B. So if we look at the left limit, it's coming in, and let's just call this 1. Same thing for both of these, kind of to make this easier. I'm just giving it some made up values. Let's say from the left, it's coming in at 1. From the right, it's coming in at 1. But what is f of -2? There is no answer. It's not defined. There's no solid dot. So because the left limit does not equal where it's defined because it doesn't exist, and the right limit does not equal where it's defined because it doesn't exist, the limits do not equal where it's defined at, this is a neither case. It is not continuous on the left. It is not continuous on the right. So at x equals -2, I would say neither. So that's what we're going to do. We're going to look at each one of these values. So now we're going to look at x equal -1. Okay? So -1, as x comes in from the left, it's going to -infinity. As x comes in from the right, it's going to -infinity. What is f of -1? There is no answer. There's no solid dot. So because again, f of -1 doesn't exist, this is going to be a neither case because the left limit and the right limit do not equal f of -1. So again, that's neither. All right, let's look at x equal to 0. So the left limit is up here at 1. Again, okay, and let's call this down here 1 or -1. So the left limit, it comes into a +1. The right limit comes into a -1. What is f of 0? It's 1. See, we got that closed out there. We actually know what it is. So if you remember, the left limit equaled 1. It is defined f of 0 at 1 because the left equals the defined. We know that this is continuous on the left. Because the left limit equals the same thing as where it's defined at. And last but not least, let's look at what happens with x equal to 1. So we'll just call this -2. And again, we'll call this a half. Since I called this 1, we'll just say this is a half. So the left limit comes into -2. The right limit comes into a half. But where is f of 1 defined at? It's right here at -1. So because the left limit and the right limit do not equal where it's defined at, this is going to be neither again. And there's all of our answers for 8. All right, number 9. Moving right along. Nothing crazy going on, promise. Yay, another graph. So we want the limit as x approaches 0, and that's going to be of f of x. Almost forgot my function. And that's going to infinity. So that right there tells us we have the possibility of a vertical asymptote. Whenever a limit goes to infinity, you have a vertical asymptote, quite possibly. And then we have a limit as x approaches 3 from the left of f of x. And that's equal to -infinity. Okay. So again, maybe the possibility of another vertical asymptote. We'll talk about that soon enough. And then we got the limit as x approaches 3 from the right of f of x equal to infinity. And then we have the limit. I should have done this one on another piece of paper because I am pretty much out of room. The limit as x goes to -infinity of f of x is equal to 3. So whenever we have whenever we have that limit going to infinities, meaning that x goes to infinity, sorry, and it equals a number, that means we definitely have some horizontal asymptotes happening. So then we got x going to +infinity for f of x, and that is equal to a -2. So we want to draw this information. So this is kind of like all about little bits of end behaviors of your function. That's really what's kind of going on with number 9. So these are all the limits that we have to make sure are being met. So continuing on to my next piece of paper, draw me a nice little graph. So let's talk about some values that we care about. Obviously, you see X values are 0 and 3. So I'm just going to come out here, 1, 2, 3. And then we have infinities, infinities, infinities. Oh, we got some Y values at a positive 3 and a negative 2. 2, 3, and 1, 2. So really, that's what our graph looks like. All right, so let's start talking about some things. So as I alluded to earlier, these top 3 right here are dealing with vertical asymptotes. Whenever you have a double-sided limit that goes to infinity, you definitely have a vertical asymptote, okay? Because on the left side, it's shooting straight up, and on the right side, it's shooting straight up. So we know that we have a vertical asymptote right here at 0. So I'm going to kind of darken in my line right here. Put some little, making it dash so you can kind of see those dashes because it blends in. And this is X equal to 0. It's a vertical asymptote because of that first limit that we had. Okay. Now, if you look at, and also because of this vertical asymptote, I know that my graph has to shoot up around it. So I'm going to put like little tick marks right there showing that my graph is going to be somehow coming up into this thing and shooting straight up. And my graph is going to come up into this thing, shooting straight up. All right. Now, when X is approaching 3 from the left, it's at negative infinity. And when X approaches 3 from the right, it's at positive infinity. Because both of these are an infinity answer, I know that this is another vertical asymptote. Just one side of my graph, the function will be shooting down, and the other side of my graph, it will be shooting up around that vertical asymptote. So let's draw that in. So we got a vertical asymptote right here at 3. So X equals 3, that is a vertical asymptote. Oh, can't see that. And we know that on the left side, my graph is down. And on the right side, my graph is up. So I make my little tick marks there. So I know what my graph is doing. It's got to shoot down on the left and shoot up on the right. Okay. And so that takes care of these. Now right here, these help us signify those horizontal asymptotes. Whenever you have X going without bound, either to positive infinity or negative infinity, and it equals an actual number, that means that you have horizontal asymptotes. So we know that we have a horizontal asymptote at 3. So I'm going to draw that in. So we got this horizontal asymptote coming in right here. And that is Y equals 3, horizontal asymptote. And we know that our function is coming in towards that, this Y value. So I'll put my little tick mark here in a moment after I do this guy. So this one, we know that X, as it goes to infinity, is going to approach -2. So we have another asymptote down here at -2. So this is Y equals -2, another horizontal asymptote. Okay. So let's talk about the horizontal asymptote piece. So we know that on the left side, it has to come in when X is entirely negative, it has to zone in on the Y value 3. So over here, you can put your mark below the line or above it. It's your call. Because remember, we can cross horizontal asymptotes. Okay. But I'm going to keep things, again, simple, the KISS idea. My mark over here at the vertical asymptote is up in this square. So I'm going to make sure that my function stays in this upper square. And I'm going to make my function hone in on the top side of my asymptote. And I'm going to connect these two. So here's what my function looks like so far. Okay. So I'm honing in on 3 as x goes towards negative infinity. And as x goes towards 0, I'm shooting up to positive infinity. Again, I could have had my graph come down, dip, and then come back up. Or I could have had my graph come down through and just hone in on the bottom side of that. It doesn't really matter. I'm just going to keep it simple. Okay. Now, in between here, I've got a mark up here and a mark down there. All you got to do is connect those because there's nothing special that we need to worry about in here. So I'm just going to take this, I'm going to draw it moving on down to my next mark. And again, it's okay to cross horizontal asymptotes. We have to in order to connect these two. All right. Now over here on this side, again, as x is shooting off towards positive infinity, let's make this just a little bit longer. As x is shooting off towards positive infinity, my limit says we're going to -2. So since my mark is up here, I'm definitely going to have to cross this no matter what. I'm going to make my ending mark right above my line here. Again, I could have made it below it. I don't have to have it always above it, but I could have made it below it where it comes down, dips, and then shoots back up towards it. But I'm just, again, I'm going to keep it simple. So here's what I believe the function looks like there. So again, I could have had it come down, dip below, and then hone in. But again, I'm going to keep it simple. And the cool thing is you can always check your picture to make sure all that is being met. There should be nothing else happening other than these limits. So there's our picture. So this one was all about vertical asymptotes, horizontal asymptotes that help you kind of draw what's going on. Okay. All right, number 10, let's go to that one. So here we're going to find the limit as x goes to positive infinity of the square root of x plus 3x squared all over 4x minus 1. Okay. So obviously direct substitution is not going to work into this because we don't have a value to directly substitute in. Okay. Factoring and all that stuff is not going to work. But remember that in this section of 2.6, that we found out that if we could create a limit as x goes to infinity of 1 over x, we knew that that answer would always be 0. Okay. So that's the trick to this. We're going to create 1 over x. And what we're going to do is we're going to divide every term up here by the highest term degree from the denominator. So when I look at my denominator, the highest term degree is x to the first. So what's really going to happen is we're going to take the limit as x goes to infinity, and we're going to multiply the top and the bottom by 1 over that degree. So again, our highest degree was x to the first, so that's why I have x to the first in the bottom. If it was x to the second, it would have been x to the second. And again, we can get away with that because this is just multiplying by the number 1. And you can always multiply by the number 1 and not change things. All right. So let's take and let's distribute through. I'm going to work with the bottom first, and then we'll talk about the numerator. So when I distribute through in the bottom, I'm going to get 4x over x minus 1 over x. And then with a little bit of cleanup, this is what you have. In the denominator, this becomes 4 over x. Okay? Minus, sorry, that doesn't become 4 over x. That just becomes the number 4. Silly Mr. Armstrong. His brain is working too fast sometimes. So I'll put the number 4 in there. Just a second. My little whiteout has to dry. And this is 1 over x. So this will just be 4. Okay? And you know that the limit of a constant, because this is 4, will just be that constant. And you will know that the limit of 1 over x will just be 0. Okay, so there will be our denominator math that we're going to do. And again, there we go. The x's canceled out where that just became 4. So the limit as x goes to infinity of a constant is just that constant. All right, now up here in the numerator, we have to move this back under the radical. So in order to move this back under the radical, you got to square it. Okay. So 1 over x, when moved under the radical, looks like this now. X over x squared plus 3x squared over x squared. Okay. Now, x over x squared becomes 1 over x. 3x squared over x squared will just become the number 3. So again, you know that the limit of this will go to 0. And the limit of a constant will go to that constant. So here's the math. So in the end, we end up with this square root of 3 all over 4 as the limit of this function as x goes to positive infinity. Yay. All right, before I write down, oh yeah, we can do number 11 at the bottom. Okay, number 11. It is asking 2 very important questions. Not hard ones, but important ones. I know it looks weird and it looks difficult because it's all these formulas, but it's not, I promise. So part A is asking, what is the slope of the secant line through the points? Okay, no worries, we can do that. So part A is all about the slope of the secant, PQ. Well, how do you find slope of a line? Well, that would be y2 minus y1 all over x2 minus x1. So plug in. So our y2 is f of x minus our y1 is f of 6. Fix my little 6 there. All over my x2 was x minus my x1 was 9. That's weird. Wait, hold on. I put f of 6 for some reason. That was my fault. That should be a 9. Silly Mr. Armstrong again. I'm like, that looks weird. That should be a 9. And that should be a 9. I don't know where I got f of 6 from. It's not in any of these pieces down here. Nope, they're all nines. Nines. Crazy, Mr. Armstrong. That happens. So this would be -9 because that's my x1. So I'll just get that in just a second to dry. Now, part B wants to know what the slope of the tangent line is. So we want the slope of the tangent at P. Well, remember when we talked about this in 2.1, that the slope of the tangent is really the instantaneous rate of change. Okay, so this is the average rate of change. When you go to the tangent, it's the instantaneous. And how do we find the instantaneous? Remember, all we did was just take the limit of the secant line. The limit of f of x minus f of 9 all over x minus 9. Now the limit, we want it as it approaches the point. Well, what's the x value of the point we care about? It's 9. So right there, taking the limit as x approaches 9 of this slope will give us the tangent line, the instantaneous rate of change. And there we are. That's number 11. Okay, number 12. Almost done. We're going to 14. So number 12, it's got a couple parts. That's all right. So number 12 says researchers measured the average blood alcohol concentration, C of T, of 8 men starting 1 hour after consumption of 30 milliliters of ethanol, corresponding to 2 alcoholic drinks. Selected values of C of T are given in the table. Round your answers to 2 decimal places. That's important. So complete parts A and B. So part A, they are wanting you to find the average rate of change. The average rate of change. So to find that average rate of change, that just means the slope between these 2 values. Now remember, this is an interval, not a point. Okay, but this is telling you what 2 points to work with. So we want to work with 1 and we want to work with 2. Well, we know 1 is up here and there's the 2. So these are the points that you're working with. And you're just going to do y2 minus y1 all over x2 minus x1. So here's our y2, 0.16, minus our y1, 0.32, all over x2 is 2.0, minus x1 is 1.0. So this is what I just said in words. y2 minus y1 all over x2 minus x1. Go to your fancy dancy calculator and figure out what the answer is. Give me just a moment. I'm working on my calculator right here in front of me. I'm not showing this work because I know that you all should be able to use your calculator. So you should have found out that this is negative 0.16. And then all we're going to do is we're just going to keep repeating this process for some other intervals. So our next interval is 1.5, comma 2.0. So the slope for this, again, you'll have 0.16 minus, this time it's 0.22, all over 2 minus 1.5. So again, there's what it looks like, what I just said in words. Coming up here, doing some quick adjusting. And we've got negative 0.12. Okay. Then we're going to do I. And I know this one is going to be from 2 to 2.5. Pretty sure. Let me double check. Yep, I was right. So this time you're going to have 0.1 minus 0.16 all over 2.5 minus 2. So again, this is what it looks like. So if I just go back, do some quick reworking. Put it in my calculator. Thank you for being patient. And we get negative 0.12. And then our last interval will be from 2 to 3. And we're going to get 0.08 minus 0.16 all over 3.0 minus 2.0. So again, there's what I said in words. Coming back in, slight modifications. And 3.0, negative 0.08. So there's part A. Here are all the average rate of change. Surrounding, if you didn't notice, 2. So these are all the secant lines. So in part B says, well, what is the instantaneous rate of change? Rate of change at t equal to 2. Okay. So the instantaneous rate of change at t equal to 2, all we're going to do is we're going to take the two closest secants, which will actually be these two right here, the two closest secants, and we're going to average their rates. Well, that's easy. Negative 0.12 plus negative 0.12 divided by 2. In the end, that will give you, so that way you can see what I just wrote, negative 0.12. So there's the instantaneous rate of change. And then it also asks you about the label. So remember that the label is all about your y values over the x values. Well, what are the y values about? They're about grams per deciliter. Your x values are all about hours. So your rate of change looks like this: grams per deciliter per hour, because this is my y value over my x value. And that is the units, or are the units, you're looking for. And it is right there. Yay. See, nothing crazy. Number 13. So we are asked to find the equation of the tangent line. And this is according to what is happening in section 2.7. Okay. So we want to find the equation of the line according to the definition that we learned in 2.7. Now we'll tell you that definition here in a second. And you've actually already kind of worked with the definition already, all the way back in question number 11. So this question number 11, what you're doing right here, when we did the slope of the tangent line piece right here, that's exactly what we're going to be doing down here. And number 13, we're going to be applying that formula. So again, that formula, the definition for the slope. So the slope of the tangent is going to equal the limit as x goes to our value that we care about, our point, x value, and it will be the limit of f of x minus f of a all over x minus a. It's the same formula that we talked about in number 11. Okay, well, let's plug in. So the limit as x goes to, what is our a value? It is 6. Okay, and so we'll have f of x minus f of 6 all over x minus 6. So this is what we're going to figure out. So I'm going to do some side work over here. Side work. So that way I don't have to keep writing limit, because that can be annoying. So we're going to figure this guy out right there. So we know what f of x is. That's our equation. So we're going to have 2x squared minus 10x plus 1. And we want to subtract off f of 6. So you could take 6 and plug it in. And if you do that, it will look like this. It's almost out of paper there. But again, you actually already know what f of 6 is. It's from our point. So plugging 6 into this, you should just get the number 13 out. So in actuality, we just have 2x squared minus 10x plus 1 minus 13. And that right there leads us to 2x squared minus 10x minus 12. And there you go. So the limit that we're really working with then over here is this. The limit as x goes to 6 of 2x squared minus 10x minus 12 all over x minus 6. Now again, we can't do direct substitution here because 6 is not in this domain. So if you go back, think about your factoring, we can factor this. The limit as x goes to 6. So up here, this piece factors to 2. X minus 6. X plus 1. All over x minus 6. Oops. Okay, because a 2 factors out of this, and then you get x minus 6 and x plus 1 as the rest of the factoring. So now you can see that the real limit we're working with, or another limit that we can actually work with, number 13, is the limit as x goes to 6 of 2 times x plus 1. And this we can direct substitute into, which gives us 2 times 6 plus 1, which gives us 14. So this is the slope of the tangent at 6, 13. Our directions are what is the equation. So as we learned, we're going to find the equation of a line, and we've got the point slope that we can work with. And I did this the other day. I started with x's. Those should be y minus y1. Armstrong's brain is not working this morning. That happens. So that's going to be y minus y1 equals, and I'll come back and fill that in, the slope of x minus x1. Okay? And remember, we already know the slope. The slope of our line that we're dealing with is 14. We already have the point as well. The point that we're dealing with is 6, 13. So we're just going to plug this information in. And that's y and y. So we got y minus y1 is 13 equal to m, which is 14, times x minus x1 is 6. So convert this to slope intercept, and you get y equal to 14x. Give me just a moment to do some quick math. And that should end up being a negative 71. And there is our equation. Of the tangent line at the point 6, 13. Yay. All right. Last problem. We did it. We made it. Number 14. It's a lot like number 12. So the first thing you're going to do is you're going to draw me a graph. You're going to plot some points. Okay. So give me just a moment to kind of replicate this graph. So, and basically what you're going to do is this shows the position of a motorcycle after accelerating from rest. So here's your time, here's your feet, and looks like we're going all the way out to 6 on the X. 1, 2, 3, 4, 5, 6, and that's in seconds. Our Y values are going pretty much up to 250. So count by 50, so 50, 100, 150, 200, 250. Okay. So all we have to do is plot these points. So I'm going to do some quick plotting real quick, and then I'll show you what my graph looks like. So we definitely have a point at 0, 0. There's a dot. We got a point at 1, 4.9. So that's barely moved. Then we got a point at 2, 10.6. So again, barely just a little bit higher. Then we got a point at 3, 23.3. So just about halfway, just above the 50 mark at 4, 50.2, 5, 109.4. So that'll be just above the 100 mark. And then at 6, we are off to the races. We are definitely a little above the halfway mark. So this is what your picture should look like, plotting those points. There you go. So kind of looks exponential. Okay. All right. So there's one piece of this. And then the last piece, it says, what is the instantaneous velocity when t is 3? Velocity. And it tells you the units, which is feet per second, at t equal to 3. So again, we've done this. You just want to look at the intervals around it, the two closest. So we want to look at the intervals from 2 to 3 and find that slope. And then we want to look at the interval from 3 to 4 and find that slope. And then we will take the average. Okay. So let me write up what my equations look like. So from 2 to 3, my y1 is 23.1 minus my y2 is 10.6. All over my x2 was 3 minus my x1 was 2. And then for the slope of the interval 3 to 4, my y2 is 50.2 minus my y1, 23.3 or 23.1. All over all over my x2 is 4 minus my x1 is 3. So here's what I just talked about, written out. We want the slope of the interval 2 to 3, and we want the slope of the interval 3 to 4. Okay. So I'm just going to go to my calculator, work these up. And also it does have rounding. It says round to 1 decimal place in the end. So make sure that in the end, we're going to round correctly. So 23.1 minus 10.6 all over 3 minus 2. So the first rate of change is 12.5. My second rate of change, so we're going from 50.2 minus 23.1 all over 4 minus 3. And that's going to be 27.1. So to get our instantaneous, all we're going to do is take 12.5 plus 27.1 and divide those answers by 2. So 12.5 plus 27.1. That will give us 39.6 divided by 2, 19.8 feet per second. There you go. There it is. And that, my friends, is the Exam 1 review. Thank you for stopping by. And until next time, you stay classy. Calculus 1.